Hey there, and welcome. Have you ever, really stopped and thought about how we see anything? I mean, everything, from a beautiful rainbow to your own reflection. It's all thanks to light, and honestly, light can be pretty weird sometimes. And the best part? We can start figuring it all out with something you probably have in your kitchen right now.
Yeah, it really all starts with something as simple as a spoon. Seriously, go grab a shining one if you can. Look at yourself in the inside part, the bit that holds the soup. Now, flip it over and look at the back. See how your reflection changes? It might even be upside down. That one little spoon, it's basically a mini lesson in some of the coolest concepts in optics. So, how are we going to crack this whole spoon mystery? Well, first we'll cover the super basics, what actually makes things visible in the first place. Then we'll get into the simple rules of how light bounces, which is called reflection. After that, we'll jump right into curved mirrors, just like our spoon, and even check out the surprisingly simple math behind it all. Then we'll switch gears and see what happens when light bends instead of bounces. And finally, we'll see where all this stuff pops up in our everyday lives. Ready? All right, let's start at the very beginning. First up, what makes anything visible? I know, it sounds almost too simple, but trust me, this is the absolute foundation for everything else we're going to talk about. It's actually super straightforward. Think about it. If you're in a pitch black room, you see nothing, right? But the second you turn on a light, that light zips out, hits all the stuff in the room, and bounces off in all directions. A little bit of that bounced light goes into your eyes, and boom, your brain turns that information into the image you see. It's all just reflected light. Okay, and for what we're doing today, the most important thing to remember about light is this. It travels in straight lines. Always. I mean, just think about a shadow. The only reason you get a sharp shadow is because the light can't just bend around an object that's in its way. This straight path has a name. We call it a ray of light. And understanding this ray is the key to everything about reflection. So if everything we see is just light bouncing around, you've got to wonder, are there rules for how it bounces? And the answer is yes, absolutely. And the best part is, the rules are incredibly simple. It's awesome. Believe it or not, there are just two simple laws for this. That's it. First, the angle that light hits a surface is the exact same angle that it bounces off. They're equals. The second law is that the incoming ray, the outgoing ray, and an imaginary line we draw straight out from the surface, we call that the normal, they all sit on the same flat surface, like three lines drawn on a single sheet of paper. And what's really amazing is that these two little rules work for everything. A flat mirror, a bumpy wall, and yep, even our curved spoon. And speaking of our spoon, that brings us perfectly into the world of curves. So let's leave flat mirrors behind for a bit and get right back to that spoon, which is a perfect real-world example of what scientists call a spherical mirror. So, with these spherical mirrors, there are basically two types. First, you have the concave mirror. Think of it like a cave. It's curved inwards. That's the inside of your spoon. This type of mirror brings light rays together, or converges them. The other type is a convex mirror, which bulges outwards, just like the back of the spoon. This one does the opposite. It spreads light rays out, or diverges them. Now, to really get a handle on how these mirrors work, we need to know a few key terms, some points of reference. Let's start with the easiest one, the pole, which we label with a P. It's just the exact center of the mirror's surface. Think of it as our starting point, our home base. Okay, next up, imagine your curved mirror is actually just a tiny piece that you sliced off a giant, hollow crystal ball. The center of that huge original ball, that's what we call the center of curvature, or C. So for a concave mirror, the one that curves inwards, C is out in front. But for a convex mirror, the one that bulges out, C is kind of behind it, inside the imaginary sphere. All right, now for the really important one, the principal focus, or F. This is where the magic happens. If you take a bunch of parallel light rays and shine them on a concave mirror, they will all bounce and meet up at this one single point. That's the focus. Now, for a convex mirror, the rays bounce and spread out, but if you trace their paths backward, it looks like they all came from one single point behind the mirror. That's the focus for a convex mirror.
And this diagram just shows it perfectly, right? Look at the left side, the rays come in, hit the concave surface, and bam, they all meet at point F. Now look at the right. The rays hit the convex mirror and scatter, but see how if you trace those dotted lines back, they all point to that single focus point F behind the mirror? It's a really neat visual.
And get this, there's a really clean and simple relationship here. The distance from the pole to the focus, we call that the focal length, f, is always exactly half the distance from the pole to the center of curvature, which is the radius r. So the formula is just r equals 2 times f. Super easy to remember.
Okay, so we've got the concepts down. But what if I told you we could use this to predict exactly where an image is going to show up and how big it'll be? Well, we can. And that's where a little bit of mathematical magic comes into play.
And this is the key to everything. It's called the mirror formula. It might look simple, but this little equation is so powerful. It connects 3 things: the distance of the object from the mirror, the distance of the image it creates, and that focal length we just talked about. It's like a secret code for mirrors.
So let's break it down real quick. U is how far the object is from the mirror. V is how far the image is from the mirror. And F is the focal length. The really cool part is if you know any 2 of these, you can always figure out the third one. It's awesome.
Okay, but there is one tiny catch. For the formula to work every time, we have to follow a set of rules. Think of it like the rules of a game. It's called the sign convention. Basically, we pretend the mirror is on a graph. The pole is the center, the origin. Anything to the left of the mirror is negative, and anything to the right is positive. And anything above the center line is positive, while anything below is negative. That's pretty much it.
And this diagram really helps make it clear. See? We always put the object on the left, so its distance, u, is always going to be negative. If the image shows up in front of the mirror, what we call a real image, its distance, v, is also negative. But if the image appears behind the mirror, a virtual image, then v is positive. As long as you stick to these simple plus and minus rules, that formula will never let you down.
All right, so we are now masters of light bouncing. That's reflection. But what happens when light doesn't bounce off something, but goes through it? Like when it passes from the air into a glass of water? Oh, this is where things get really, really cool. This bending of light is called refraction. You've totally seen this before. It's why a straw or a pencil in a glass of water looks like it's bent or even broken right at the water's surface. What's happening is that the light coming from the underwater part of the pencil actually changes direction when it leaves the water and enters the air to reach your eyes. Our brain just assumes light travels in a straight line, so it gets tricked. It makes the pencil look like it's in a different spot than it really is. How cool is that?
So we've looked at reflection and we've just touched on refraction. You might be wondering, okay, but why does any of this matter? Well, it matters because these ideas are literally everywhere. They're built to the technology we use every single day. Just think about concave mirrors, the ones that curve inward. They're in our torches and car headlights, taking light from a small bulb and focusing it into a strong beam. Even dentists use them to get a nice, big, magnified view of your teeth. And then there's convex mirrors, the ones that bulge out. They are perfect for the side mirrors on cars. Why? Because they always give you an upright image. Plus, they show you a huge area behind you, which is exactly what you want for staying safe on the road, right?
You know, we've spent all this time talking about light as a simple straight line, a ray. And that works perfectly for figuring out mirrors and lenses. It really does. But I want to leave you with a final thought. In the much deeper world of physics, light is, well, it's way weirder than that. Sometimes it acts like a wave, and other times it acts like a particle. This whole ray idea is just a really useful story we tell ourselves. It's a great reminder that even in the most ordinary things, there are amazing mysteries just waiting. So I'll leave you with this question. What do you think light really is?